Welcome to Talk Tensors. Today we are unpacking something that it really feels like a genuine turning point. You know, usually when we talk about reasoning models or system 2 thinking in AI, we're talking about these massive proprietary systems.
Right, behind very high walls.
Exactly. You're thinking OpenAI's O1, the huge clusters you need for something like DeepSeek. I mean, we picture billion-dollar data centers, cooling fans the size of jet engines.
And algorithms so complex you need a PhD just to get through the abstract.
It's always this don't try this at home kind of situation.
Absolutely. The assumption has always been that, reasoning is a luxury feature. It's reserved for the heavyweights with the deepest pocket.
Exactly. But today, we're looking at a paper that basically just says, hold my GPU.
It really is a hold my beer moment for the open source community, yeah.
We are diving deep into a paper titled Open Reasoner Zero, an open source approach to scaling up reinforcement learning on the base model. The acronym here is ORZ.
ORZ, yeah.
And if you've been anywhere on X or Reddit lately, you've seen the charts, you've seen the hype. But we are going to look past the viral tweets and really figure out what is actually happening under the hood.
We have to, because the implications here they're massive.
They really are.
And what's happening is, I think, a fundamental shift in how we even think about training these models. We aren't just fine-tuning them to, copy human answers anymore.
We're moving past that.
We're entering the era of Reasoner Zero.
Reasoner Zero. It sounds like a sci-fi movie title.
It does, a little bit.
But it's actually a specific training paradigm. So before we get into the math, and fair warning to you listening, we really represent the deep dive today. So we will get into the math. Can you just set the stage for us?
Sure.
Why is everyone losing their minds over Open Reasoner Zero right now?
Okay, so it really comes down to two things: accessibility and efficiency. Until now, if you wanted to replicate something like DeepSeek R10, which was kind of the previous gold standard for open weight reasoning models, you needed just a massive amount of compute.
Right.
And a very, very complex pipeline. You need a whole cluster of H100s that most startups, let alone universities, just don't have access to.
Right. DeepSeek was a breakthrough, for sure, but it was a heavy breakthrough. It sort of showed us the door was open, but the door handle was like 10 feet off the ground.
That's a great way to put it. Exactly. What ORZ demonstrates is that you can get those same aha moments, those really complex reasoning chains where the model actually stops and thinks, using a minimalist approach. They took a base model, QuAn 2.532b, and turned it into a math wizard using roughly 1/10 of the training steps that previous methods required.
Wait, 1/10? That's not an optimization. That's an order of magnitude shift.
It is.
That changes the entire economics of the field. I mean, that means you can train a state-of-the-art reasoning model on a budget that doesn't require a sovereign wealth fund.
It does. And the most shocking part isn't just the speed. It's how they did it. They did it by stripping away almost all of the complex tricks that reinforcement learning engineers usually swear by.
What do you mean?
They didn't use fancy formatting rewards. They didn't use KL regularization, which is, that's usually the safety rail for these things. They went back to absolute basics.
And it worked better.
It worked better.
So this is the minimalist revolution we put in the title. The thesis here is basically stop overthinking the training process. If you set the incentives right, the model just figures it out.
Precisely. The paper proves that a minimalist approach, specifically using, vanilla PPO algorithms and simple binary rewards, is actually the key to scaling reasoning. It's moving us from imitation learning,
where the model just mimics a human.
Right, to genuine reinforcement learning, where the model discovers its own strategies to solve problems.
Okay, I want to drill down on that. Let's unpack this Reasoner Zero concept. We hear zero attached to everything and AI zero shot, AlphaGo zero. What does Reasoner Zero specifically mean in this context?
So in this paper, Reasoner Zero refers to training a large language model to master really complex reasoning. We're talking math, logic, coding via reinforcement learning, or RL,
right,
without relying on massive amounts of supervised fine-tuning or distillation first.
Okay, let's clarify that difference. Usually the standard recipe, the whole Instruct GPT recipe we've been using for years, it starts with supervised fine-tuning, or SFT.
Correct. And SFT is basically showing the model thousands and thousands of examples of humans solving math problems step by step. You say, here's a problem, here's exactly how a human solves it. Copy this style.
You're teaching it to mimic.
You're teaching mimicry. You're effectively saying, do as I do.
It's kind of like tracing a drawing. You learn the lines, but you might not understand the underlying form.
Right.
You're learning the syntax of the solution, but not necessarily the logic.
That's a perfect analogy. In Reasoner Zero, you skip the tracing entirely. You take the base model, in this case, QuAn 2.532b, which is just a raw autocomplete engine.
Right.
It's read the internet, but it hasn't been taught how to behave or solve specific math problems in a structured way. And you throw it into the deep end with reinforcement learning.
So you just give it a problem, you let it try to solve it, and you simply tell it correct or incorrect.
Yes. It feels a bit like throwing a kid into a pool to teach them to swim.
Yeah.
But apparently, if the kid is a 32 billion parameter neural network, it learns to swim way faster than if you gave it swimming lessons first.
And the choice of base model here is important. They chose QuAn 2.532b. Why that one specifically?
Well, QuAn has really established itself as a very strong foundation. It's a dense model, it's well-trained on a huge corpus, and it's open weights. But the key thing for this experiment is that they used the base version, not the instruct-tuned version.
Got it.
The whole mission of the ORZ project was to see if they could make this raw model scalable and robust using only RL.
It's like buying a plot of land instead of a pre-built house. You want to see if you can build the structure yourself from the ground up to make sure the foundation is exactly what you need for reasoning.
Exactly. And previous attempts, like that DeepSeek R10 paper, they showed this was possible, but like you said, it was heavy.
And unstable, wasn't it?
Wow.
I remember reading that some of the early R10 models had some weird quirks.
Very heavy and very unstable. We'll get into the instability later, but yeah, often these models would just collapse into gibberish. You'd run the training for a week, you'd come back, and the model is just printing the letter A 5,000 times.
Oh, wow.
Or it gets stuck in a loop of let's think. The mission of ORZ was to democratize this, to make a recipe that a university lab or a smaller startup could actually run without burning through their entire VC fund on the electricity bill.
And the stats. They're undeniable. On benchmarks like AIM 2024, which is a really hard math competition, we're talking high school Olympiad level.
Very hard.
And GBQA Diamond. ORZ is getting superior performance to the DeepSeek equivalent, but again, with just a fraction of the training steps.
It's just a cleaner, faster path to intelligence.
Okay, so we have a faster, smarter, simpler model. Now we need to know how, because this is where we have to get technical. The choices they made here really go against the grain of what's trendy in AI right now.
They do.
I mean, if you look at the open source Discord channels, everyone is obsessed with one particular algorithm.
Oh, yeah. Everyone is talking about GRPO.
GRPO group relative policy optimization. It's the darling of the moment. But ORZ said, no thanks, and went back to vanilla, PPO, proximal policy optimization.
Why?
Why go back to the older tech? Is this just retro nostalgia?
No, it's definitely not nostalgia. It's about stability. And to understand this, we have to talk about the critic.
The critic? Okay, lay it out.
In reinforcement learning, specifically in PPO, you typically have two main components, an actor and a critic.
Right.
The actor is the model that's actually generating the text. It's the writer. The critic is a separate neural network, or sometimes it's a separate head on the same model, and its only job is to look at the state of the conversation and estimate the value.
So the actor says, I think the answer is 42, and the critic says, what exactly?
The critic looks at all the steps taken so far, and it estimates how likely are we to get a reward from this point forward. It's a value function. It's trying to predict the future. It's constantly assessing the current situation to see if the actor is on the right track or, driving off a cliff.
So the actor is the writer, and the critic is the little editor sitting on their shoulder, constantly grading the probability of success.
That's it exactly. Now, GRPO, the trendy new method, gets rid of the critic.
Why?
Well, the main reason people love GRPO is that it saves memory. Maintaining a second model, the critic, takes up a lot of VRAM. So if you get rid of it, you can fit a bigger actor model on your GPU.
That makes perfect sense. I mean, VRAM is the scarcest resource in the universe right now. People would sell their grandmother for more HBM. So GRPO ditches the critic. How does it learn then?
So instead of a critic, GRPO generates a whole bunch of answers. Let's say 8 different attempts at the same problem.
Okay.
It then compares them to the group average. If attempt number 3 was better than the average of all 8, it gets a gold star. If it was worse, it gets punished.
That sounds pretty efficient. It's like peer review for an AI. Why is that a problem?
It is efficient, but it struggles with what we call credit assignment. Imagine the model is solving a hard math problem. It writes 3 paragraphs of absolute gibberish, just repeating the word wait, but then by total random luck, it guesses the right number at the very end.
Okay, so it fluked it. It just hallucinated its way to the correct integer.
Right. If you're using GRPO, the algorithm sees that final right answer and says, great job, do more of that. It reinforces the entire chain of thought, including all the gibberish. It reinforces the wait part because it doesn't have a granular way to distinguish the good steps from the bad ones.
I see. So it can't tell the difference between I solved this intelligently and I just spammed a bunch of text and got lucky.
Yeah.
It's totally outcome dependent, not process dependent.
Exactly. And this leads to a very common failure mode called collapse. The paper talks about this explicitly. Without a critic, GRPO models often fall into these repetitive loops. They'll just repeat a phrase endlessly because, statistically, they can't distinguish the noise from the signal.
And so the noise of the gibberish gets reinforced right alongside the correct answer.
It does. Now, the PPO advantage.
Yeah, what does PPO do differently?
The PPO advantage is that the critic is learning right alongside the actor. And the paper shows this beautifully in their analysis. The PPO critic specifically learns to identify those repetitive loops.
But how does it know they're bad if the answer ends up being right sometimes?
Because historically, throughout the entire training run, whenever the model starts looping wait, it usually fails or runs out of tokens. The lucky guess is the rare exception. So the critic learns, hey, I've seen this pattern before. This pattern leads to a reward of 99% of the time.
So when the actor starts looping,
the critic's value function drops like a stone. It basically says, I recognize this pattern, this is garbage, cut it out.
So the critic creates a negative advantage for those looping tokens in the moment. It punishes the model for stalling or looping, even if it might eventually get the answer right by chance.
In a way, yes. It stabilizes the whole training process. It prevents that collapse. The authors show that the critic effectively learns to devalue these repetitive nonsensical patterns. That's why ORZ is so much more stable than the GRPO attempts. They sacrificed a little bit of VRAM to keep the critic, and it paid off with massive stability gains.
That is fascinating. It's like having a teacher who doesn't just grade your final answer, but actually walks around the room, looks at your scratch pad and says, hey, stop doodling. Get back to the actual problem.
That is the perfect analogy. GRPO is just checking the answer sheet at the end. PPO is checking the work as it happens. And when you are trying to teach reasoning, checking the work is everything.
Now, sticking with the math for just a second, and I promise you listening, we'll get back to the cool emergent behaviors in a moment, but the paper mentions some specific hyperparameter magic that I think is crucial. They talk about GAE, generalized advantage estimation. And they set these Greek letters, lambda and gamma, to 1.
This is a bold move. I mean, it sounds like a tiny detail, but it's really a philosophical stance on their part.
Usually researchers are tweaking these like crazy. A lambda of 0.95 versus 0.98 is the subject of like heated debates in labs. Why just set them both QuAn? That seems almost too simple.
It is simplistic, and that's the whole point. Let's unpack gamma first. So gamma is the discount factor. Usually in RL, you set gamma to something like 0.99. Right. And that tells the model, rewards you can get right now are worth more than rewards in the distant future.
Yeah, it's basic economics. $1 today is worth more than $1 next year because the future is uncertain.
Exactly. But does that logic actually apply to a math problem?
I guess not. The only thing that matters is getting the right answer at the end. It doesn't matter if I get it in 5 seconds or 50 seconds, as long as it's right. The correctness doesn't degrade over time.
Precisely. In these kinds of reasoning tasks, the intermediate steps are just a means to an end. You shouldn't incentivize the model to finish early just to get its rewards sooner. You want it to take as many steps as it needs.
So by setting gamma to 1, they're saying
no discounting. The final answer is the only thing that matters, no matter how long your chain of thought is.
That forces the model to look at the whole reasoning process as one single unified effort.
Correct. And then there's lambda. Lambda controls the bias variance trade-off. Usually you lower lambda to reduce variance because RL data can be really noisy. But here they have massive amounts of data and a very clear reward signal.
It's just 1 or 0.
Exactly. So they can afford to set lambda to 1, which essentially removes the bias from the advantage estimation.
So by setting both to 1, they basically simplify this massive, scary RL equation down to something like advantage equals just the final reward minus the current value.
It becomes incredibly simple and clean. The advantage is just the final outcome minus what you expected. It captures those long-term dependencies you need for multi-step math problems without any of the muddying effects of discounting or biasing. It's mathematically pure.
It's minimalist. We're only sensing a theme here.
That is the theme. Strip away the complexity, trust the data. If the math implies an infinite horizon, use an infinite horizon. Don't discount the future just because that's what we did for Atari games in 2015.
Speaking of stripping away complexity, let's talk about the no KL shock. This one really surprised me when I was reading the paper.
Yeah, that's a big one.
If you read any standard RLHF paper reinforcement, learning from human feedback, you always see KL regularization. It's the seatbelt. It's the law. And ORZ they just deleted it.
They deleted it entirely. And this is a huge departure from the norm. Usually, KL divergence is used as a penalty. It penalizes the model if it drifts too far from the original reference model.
Right. You want the model to be helpful, but you don't want it to forget how to speak English in the process. You don't want it to start speaking in binary code or some weird slang. It needs to stay grounded.
Exactly. But think about the goal here. The goal is reasoner zero. We want the model to discover new reasoning pathways. We want those aha moments.
Okay.
If you shackle the model to the base model's probability distribution using KL, you are fundamentally limiting its exploration. You're telling it, be smart, but don't be too different from what you were yesterday.
That's a contradiction. If the base model couldn't solve the problem to begin with, and you constrain the new model to be just like the base model, you're preventing it from ever solving the problem.
You are. It's like telling a student, solve this calculus problem, but you can only use the vocabulary of a kindergartner. It just limits the solution space. By removing that KL constraint, they allowed the model to drift as far as it needed to go to find the solution.
But doesn't that make the training dangerous? I mean, doesn't the model just go feral?
It can, but because they use PPO with that trusty critic, the training remains stable. And practically, removing KL simplifies the pipeline immensely. You don't need to keep a whole separate reference model loaded in GPU memory.
Which saves a ton of VRAM.
A ton of VRAM. It makes training faster and cheaper.
But wait, if there's no penalty for drifting, and the reward is just right or wrong, how are they grading this thing? Is there some complex neural network judge checking the answer?
No, and this is what they call the format discovery. The reward function it's shockingly simple. It's just a rule-based binary reward.
Okay, lay it out for me. How does a simple algorithm grade a complex math proof?
It doesn't grade the proof. It only grades the final result. There are two rules. Rule 1, did the model output the final answer between these special answer tags?
Yeah.
Rule 2, does the number inside those tags match the ground truth exactly? If yes to both, the score is 1. If no, the score is 0. That's it.
That is brutal. It's completely pass-fail. No partial credit.
None whatsoever.
And here's the fascinating discovery, right? Because in other papers, like DeepSeek or even some of OpenAI's earlier work, they often include a format reward. They give the model a little cookie just for using the think tags correctly, even if the final answer is wrong.
Right, like training wheels. Good job, you put the tags in the right place, here's a small reward. They thought you had to teach the model how to structure its thoughts.
But ORZ found that was completely unnecessary. They didn't reward the formatting at all. The base model naturally adopted these structures, the think tags, the step-by-step breakdown, simply because doing so was the most effective way to maximize its chance of getting the final correctness reward.
Whoa, hold on. So the model learned to think, not because it was told to think.
No.
But because thinking helped it get the right answer more often.
Exactly. It realized on its own, if I just guess an answer, I usually get a 0. But if I use this scratchpad space inside the think tags to work it out step by step, I get a 1 more often. It's emergent behavior driven purely by the incentive structure.
That feels profound. We aren't forcing the architecture of thought onto the model. The architecture of thought is emerging as a winning strategy.
Ideally, yes. It suggests that reasoning is an attractor state for these large models. If you give them a hard enough problem and a simple binary incentive, they will converge on reasoning because it's the optimal path to the reward.
But to get that kind of convergence, you need good fuel. Garbage in, garbage out, right? You can't just feed it random internet comments and expect it to learn calculus. What was the data strategy here?
They were very, very careful. They curated about 57,000 specific problem answer pairs.
57,000? I mean, that doesn't sound like big data in the LLM world. We're used to hearing about trillions of tokens.
For RL, quality matters way more than quantity. And these weren't just any problems. They pulled from AIM, Math, Numina Math, OpenR1 Math 220K.
So high quality sources.
Very high quality. But the curation is the key. They filtered extensively.
Okay, so what did they cut?
First, they removed proof-oriented problems.
Why? Proofs seem like pure reasoning. That feels counterintuitive.
They are, but think about it. How do you grade a proof with a simple rule-based reward? A proof is text. It's nuance. It's logic. Checking if a number matches the answer key is easy and objective for a script to do. Checking if a paragraph of logical deduction is sound is very, very hard.
Ah, I see. If your reward signal is noisy or subjective, the RL fails. You need that crisp yes-no signal. If the grader is confused, the student will be confused.
Exactly. They needed verifiable rewards. So they stuck to problems with clear, definitive numerical answers. They also used LLM-based filtering to remove problems that were too easy or too hard.
The Goldilocks zone.
Right. If a problem is too easy, the model doesn't learn anything. It just auto-completes the answer. If it's impossible, the model never gets a reward, so the gradients never update, and it learns nothing. They needed to keep it in that zone of proximal development.
Right. Challenging, but not impossible.
And they did an ablation study that proves the data size really matters. They compared training on just 7,500 samples versus the full 57,000.
And what was the result?
7.5K run just plateaued early. It learned a little bit, then it just stopped improving. The 57K run, on the other hand, showed continuous improvement in both reward and response length, all the way through training.
Which suggests we haven't even hit the ceiling yet. More high-quality data will likely yield even smarter models.
Probably. They also tested language, right? English versus a mix of English and Chinese.
They did. And this connects back to that whole stability issue we talked about earlier. They found that the English-only data was more stable. The mixed language data actually caused some instability in the training.
Why would that be? Is the model just biased towards English?
Not necessarily. It's more likely about the complexity of the prompts. They referenced findings from the OpenR1 paper suggesting that some of the Chinese math problems had simpler, less complex prompt patterns.
Okay.
So if you mix those simple patterns with more complex English patterns, the variance of your data increases. The RL algorithm then struggles to find a consistent policy that works for both. By sticking to English only for this experiment, they reduce the variance and stabilize the training.
It's all about reducing the noise so the signal can get through cleanly.
Precisely. It's like controlling the variables in a lab experiment to make sure you're measuring what you think you're measuring.
Okay, so let's look at the scoreboard. We've built the machine. We've fueled it with 57,000 curated math problems. We've taken off the safety rails, the KL. We have this minimalist PPO setup with a critic. What actually happened during training?
The staling phenomenon happened. If you look at figure 2 in the paper, and for everyone listening, just try to visualize a graph with two lines going up and to the right in almost perfect unison.
Okay.
One of those lines is the average reward. That's the model getting smarter, getting more problems right. The other line is response length.
So as the model gets smarter, it talks more.
It thinks more. The response length is almost entirely composed of tokens inside those think tags. The harder the problems it learns to solve, the more steps it writes out for itself.
It's showing its work.
It is. And the analysis of the text it generates is fascinating. It starts generating these reflection words. Words like wait, recheck, alternatively, however.
And these weren't explicitly in the training data.
Yeah, no, not forced at all. The model learned that stopping to generate the token sequence, wait, let me recheck that last calculation, actually increased the probability of getting the final reward. It's learning self-correction in real time.
That is the aha moment. It's learning to doubt itself. That's a very high level of cognitive function, or at least a very convincing simulation of it.
And there's a really cool detail about the 32B model specifically. In the training curves, the response length for the 32B model starts fluctuating wildly at one point. It goes up and down and up and down.
But the reward?
The reward just keeps going steadily up.
What does that mean?
It suggests the model was actively experimenting.
Yeah.
It was trying out different reasoning strategies. What happens if I think for a really long time? What if I try a shortcut? It was exploring the solution space, searching for the most efficient path.
Wow.
The smaller models, like the 7B and 1.5B, they just went up linearly. The 32B model had enough capacity to actually brainstorm different approaches before converging.
That feels incredibly human.
Yeah.
You know, maybe I'm overthinking this. No, wait, maybe I'm underthinking it.
Exactly. And the final results speak for themselves. On AME 2024, the ORZ 32B model hits 48.1%. For context, the equivalent DeepSeek R10 model, trained on the same QuAn base, hits 47.0%.
So it beats it.
It edges it out. But then on Match 500, it hits 92.2% versus DeepSeek's 91.6%. On GBQA Diamond, which is graduate level science questions, it hits 55.5% versus 55.0%.
So it's winning pretty much across the board.
It is winning. But remember, the real victory here isn't that extra 1% of accuracy. It's that it achieved this in a tiny fraction of the training steps. It's the efficiency. It proves you don't need the massive, messy, complex pipeline that DeepSeek used. You can do this cleanly and quickly.
And this isn't just for the big models, right? You mentioned they tested this on smaller ones.
Yes, and this is maybe the most important part. They showed this exact same recipe works on 0.5b, 1.5b, and 7b models too. It's a universal recipe. You can take a tiny model that could run on a laptop and teach it to reason better using this exact method.
That is the Linux moment part you mentioned. You release the code, you release the data, you release the recipe.
And suddenly everyone can build their own reasoner.
And they released everything. The code, the data, the model weights. And this is crucial. They also released the critic model.
Why is releasing the critic so important? Usually people just release the final policy model, the actor.
Because the critic contains the intuition of the entire training run. It knows what a bad thought looks like. It knows what a promising path looks like. Having the critic allows other researchers to analyze why the model learned what it learned. It unlocks a whole new layer of interpretability research.
So ORZ has basically handed the entire community a blueprint. They're saying, here is how you build a reasoner, now go make it better.
That's the message. And because it just uses vanilla PPO, it's compatible with all the standard RL libraries out there. You don't need to write custom CUDA kernels to run some weird new algorithm. You can just fire up the standard tools you already know.
It lowers the barrier to entry significantly.
Drastically.
Okay, so I think we have a really solid grasp on the what and the how. We have this minimalist architecture, PPO, simple binary rewards, no KL safety rails, and it's producing state-of-the-art reasoning at a fraction of the cost.
Right. Now, I want to pivot because this paper is exciting on its own, but what keeps me up at night is thinking about where this goes next. We're seeing these incredible emergent behaviors, reflection, self-correction, strategic exploration.
It opens up a lot of doors.
It does. And that brings us to our favorite segment of the show.
I know what time it is.
It is time for Novel Notions.
Lex. All right, let's hear them.
Disclaimer time. This is the part of the show where we take the facts of the paper and we extrapolate. These are not claims made by the authors. This is purely speculative for entertainment and thought provocation purposes only. So please do not build your next startup based solely on what we are about to say.
Or do, and cut us in on the equity.
Laughs. Fair deal. I accept those terms. I've got two notions today, and I want to start with one that's based on that critic we spent so much time talking about.
Okay, I'm listening.
Notion number one, the critic-guided inference engine.
Ooh, okay.
So the paper proves that the PPO critic is incredible at detecting bad patterns. It knows when the model is looping. It knows when it's writing garbage. It assigns a low value to that state immediately.
Right. It's the teacher walking around the room spotting the doodling.
Exactly. But currently, we only use that teacher during training. Once the training is done, we fire the teacher. We just deploy the student model, and it generates text unsupervised.
Correct. Inference is usually just the policy model running solo.
But why? Why not bring the teacher to the test?
Go on.
Imagine a lightweight critic model that runs alongside the main agent during inference. As the agent is thinking inside the think tags, the critic is monitoring the value function in real time.
Like a heart rate monitor for the thought process.
Exactly. The agent writes a sentence. Okay, let's assume x equals 5. The critic says, value is high, we're on a good track. The agent then writes, therefore 5 equals 7. The critic sees that logical error, and the value function plummets.
Boom. Catches it right there.
And instead of letting the agent continue down that bad path for another 500 tokens, generating a completely wrong proof, the critic interrupts. It could force a special, wait, let me rethink token. It prunes that branch of the probability tree immediately.
So you're proposing a kind of self-healing reasoning chain.
Yes. If the value drops below a certain threshold, you abort that line of thought. You backtrack. You force a retry. You effectively save a ton of compute because you aren't generating wrong answers.
And you increase accuracy because you catch hallucinations the moment they happen, not at the end of the generation.
That is actually very plausible. The paper explicitly says the critic learns to identify garbage tokens. And since they released the critic model, you could theoretically distill that critic into a tiny, fast model, maybe a 0.5b model, that acts as a real-time supervisor for a giant 70b model.
Exactly. It's the Jiminy Cricket protocol. A little conscience for the AI whispering in its ear.
And it solves a huge problem with test-time compute scaling. We worry about models thinking for too long. A critic-guided inference engine would ensure it only thinks as long as the thoughts are valuable. The second the thoughts become low value, it just cuts them off.
Efficient, self-correcting, and robust. And it's entirely possible with the artifacts that were actually released in this paper.
Right.
I love it. It's a really smart application of the components they've already built. Okay, what's your second notion?
Okay, notion number 2, the zero-shot language expansion.
All right, where are we going with this one?
So the ablation study showed that English-only data was more stable, but it was more stable for now. And why? Because base model already knows English really well. It's the path of least resistance.
Right.
But the rewards are binary, 1 or 0. The model doesn't get points for good grammar. It doesn't get points for being polite or poetic. It just gets points for the right answer. And we saw that it adopted the think tags naturally. It adopted the structure that helped it win the game.
Yes.
So what if we trained a model on a purely symbolic language? I'm talking formal logic, code representations, mathematical notation, absolutely no natural language to start with.
Okay. A purely logical foundation.
And then we just give it the binary rewards for solving problems.
You're suggesting the model might, invent its own language for thought?
I'm predicting that inside those think tags, English is actually inefficient. English is messy. It's filled with synonyms, ambiguity, idioms.
It's a very low bandwidth way to transfer pure logic, that's for sure.
So if we run this ORZ recipe long enough, with enough compute, and with no constraint to be human readable inside the thought tags, I think the model will invent machinese.
Machinima.
A pigeon language. A hyper-efficient mix of token IDs, logic symbols, and compressed mathematical concepts that is 100 times more information dense than English. To us, it'll look like total gibberish. It'll just look like loop fail x5 gamma refactor.
Right.
But to the model, it's pure high-density reasoning.
That creates a complete black box reasoning step. We would have no idea how it got from the problem to the solution.
We would. But what if it boosts accuracy by 20%? What if it cuts the token usage in half?
It would effectively decouple reasoning from communication. The model would think in machinese and then just translate the final answer back into English for the human user.
Exactly. We are assuming that chain of thought needs to be in English because we want to read it. But the model doesn't care about us reading it.
Yeah.
It only cares about the reward. And English might be a suboptimal, inefficient strategy for maximizing that reward.
That is a wild thought. It suggests that by forcing our models to show their work in human language, we might actually be holding them back from their peak intelligence.
We might be the bottleneck.
That is a very humbling thought to end on.
It is. But that's the beauty of what OpenReasoner Zero has unlocked. By stripping away all the rules, we might finally find out what these models really want to do when we're not looking.
And now that it's all open source, someone out there can actually run that experiment.
Exactly. The tools are out there, the paper's out there, the weights are on Hugging Face.
Go clone the repo.
All right, that's a wrap for this deep dive into OpenReasoner Zero. A minimalist revolution that uses PPO, simple rewards, and raw curiosity to beat the benchmarks.
It's the Linux moment for reasoning models. It's here.
Thanks for listening to Talk Tensors. Keep your gradients clipped and your rewards high. We'll see you in the next deep dive.
Goodbye, everyone.